Hello friends, welcome to the session real line and bounded sets on the topic real analysis. Myself Soumya, 2 years, assistant professor, Government First Grade College, Tettur. With these sessions we should deal with the real line, bounded sets, supremum and infimum of sets, compactness property of the set R. So definition of the real numbers. A real number. What is a real number? A number which is either rational or irrational number is called a real number. So the set of all real numbers means it contains either rational number or the real number, and it is denoted by the set R equal to the set of rational numbers Q union the set of irrational numbers Q dash. Next we shall see the properties of real number, the field properties and order properties of real numbers. So here we have the properties of addition. The first property is the closure property. For all any two elements A and B in the set of real numbers, if A plus B belongs to R, then we can say that addition satisfies the closure property on the set R. The next property is the commutative property. For all A comma B belongs to the set of real numbers R implies if A plus B equal to B plus A, then we say that addition satisfies the commutative property on the set of real numbers R. The next property is the associative property. We shall consider three elements A comma B comma C on the set of real numbers R, which implies A plus B plus C equal to B plus A plus C, which satisfies the associative property. And next we have the additive identity. So additive identity, for all A belongs to the set R, there exists the number 0 in the set of real numbers such that A plus 0 equal to 0 plus A, and which is equal to A. Then we call 0 as the identity element or the additive identity in the set of real numbers R on the addition sign. And additive inverse. So additive inverse, again we consider an element in the set R. There exists minus A in the set R such that A plus of minus A equal to minus A plus A, which is equal to 0. A plus of minus A plus minus A plus A equal to 0. Then we call minus A as the inverse element of the element A. Next we have the properties of multiplication. So as we define the properties of addition, similarly we shall define the properties on the operation multiplication. The same property, the closure property, for all A comma B belongs to R, A into B also belongs to R. If that satisfies, then we can say that multiplication is satisfied in the closure property on the set R. And again the commutative property, for all A comma B belongs to R, then if A into B equal to B into A, then we can say that the commutative property on multiplication is satisfied. Then we have the associative property, for all A comma B comma C belongs to R, A into B into C equal to B into A into C, which is the associative property on multiplication. And we have the multiplicative identity. For all A belongs to R, there exists an element 1 belongs to R such that A into 1 equal to 1 into A equal to A. Then we call 1 as the multiplicative identity. 1 is the identity element in the binary operation multiplication. Then we have the multiplicative inverse. So for all A belongs to R, there exists a non-zero 1 by A belongs to R such that A into 1 by A equal to 1 by A into A. Then we call as 1 by A as the inverse element of A. We have now the distributive property or the distributive law. for all a comma b comma c belongs to R implies a dot b plus c equal to a dot b plus a dot c, which implies d plus a dot c equal to a dot c plus b dot c, which is the distributive property. And we have the definition of the algebraic structure. A non-empty set with one or more compositions or the binary operation or the operator defined on it is called an algebraic structure or the algebraic system. So, definition of a bounded set. We shall see the definition of a bounded sets. So, bounded set, here we have the set is bounded above or the set is bounded below. So, first we shall see what is the bounded above set. So, let S be a subset of real numbers. Let S be a subset of the real numbers. The set S is said to be bounded above. The set S is said to be bounded above if there exists a real number k, if there exists a real number k such that x is less than or equal to k for all x belongs to S. Then k is called the upper bound of S. Then k is called the upper bound of S. Similarly, we shall see the set bounded below. Let S be the subset of real numbers. Then the set S is said to be bounded below. Then the set S is said to be bounded below if there exists a real number k such that x is greater than or equal to k for all x belongs to S. Then k is called the lower bound of S. So, the set S is said to be bounded if it is bounded above as well as bounded below. So, the set S is said to be bounded if it is bounded above as well as bounded below. Hence, when a set S is bounded, there exist two real numbers, small letter k and capital letter k. There exist two real numbers, small letter k and capital letter k, such that x lies between the lower bound and the upper bound, where small letter k is the lower bound and capital letter k is the upper bound. So, the element x of the bounded set S lies between the lower bound and the upper bound for all x belongs to S. Example, every finite set is bounded above as well as below. So, it is said to be a bounded set. We shall see the theorems on this. So, if modulus of x denotes the absolute value of x, then prove that modulus of x equal to square root of x square. So, if modulus of x denotes the absolute value of x, then we need to prove that modulus of x equal to the square root of x square. So, we shall see the proof. Proof as follows. Modulus of x, we shall define the modulus of x as f of x, which is equal to plus x when x is greater than or equal to 0, and it is equal to minus x when x is equal to 0. So, the modulus of x is defined as f of x is equal to positive x if x is greater than or equal to 0, and it is equal to minus x if x is less than 0. Now, modulus of x whole square. So, modulus of x whole square equal to x square. Then, x equal to plus or minus, we shall take the square root for the equation. So, square and root cancel, x is equal to plus or minus square root of x square. Since the modulus of x is greater than or equal to 0, rejecting the negative sign, we have modulus of x equal to square root of x square, which is the proof of the theorem. And the next theorem we have is, if x and y are any two real numbers, then we need to prove that modulus of x into y is equal to modulus of x into modulus of y, and modulus of x plus y is less than or equal to modulus of x plus modulus of y. So, here we take the two real numbers x and y. We need to prove that product of x and y, absolute value of product of x and y is equal to modulus of x absolute of x into absolute of y, and absolute of x plus y is less than or equal to absolute of x plus absolute of y. So, we shall see the proof. So, first we shall consider the proof for the first one, modulus of x into y. In the previous theorem, we have proved that modulus of x is equal to square root of x square. So, applying the same here, modulus of x into y equal to square root of xy whole square. So xy whole square can be split into square root of x square and square root of y square. So square root of x square, in place of square root of x square we shall write modulus of x, and in place of square root of y square we shall write modulus of y. Therefore LHS modulus of x into y will be equal to modulus of x into modulus of y, which is the proof for the first result. And for the second one, modulus of x plus y. From the previous theorem itself, we shall write modulus of x plus y equal to square root of x plus y whole square. Expanding x plus y whole square, we know that a plus b whole square can be expanded as a square plus b square plus 2ab. Similarly, x plus y whole square, we can write it as inside the square root x square plus y square plus 2xy. So which is equal to, again we shall write modulus of x whole square, square root of modulus of x whole square plus modulus of y whole square plus 2 into modulus of x into modulus of y. So which is equal to, again, modulus of x plus modulus of y whole square. So square and roots gets cancel. We will get a modulus of x plus modulus of y. Therefore modulus of x plus y will be less than or equal to modulus of x plus modulus of y. And these are the references for you. Thank you.